Hey there folks, and welcome to another episode in the Geology 101 video series, Physical Geology. I'm Geology Professor Shawn Willsey. Thanks for joining me. Today we're on episode 14 looking at weathering. And so this video series, the Geology 101 series, is based on my college course I teach. Same curriculum, same content, same lectures and classroom discussions that I have. The only thing missing here, of course, are the labs and the field trips, but you can supplement those a bit with some of my other videos on my channel. So thanks again for joining me. Today what we're going to do is look at processes related to weathering, and that'll set us up nicely as we go into our next section on sedimentary rocks. Up to this point, we've looked at igneous rocks, how igneous rocks form, talked about volcanoes, and now we're going to look at a fundamental process in the rock cycle, and that is the breakdown of rocks near the surface, or what is known as weathering. So the first thing I think that's important is differentiating weathering from erosion. Those are two terms that I commonly see people interchange a little bit, and while seemingly innocuous, there is some big differences between these two that I want to highlight. So weathering is breaking rocks down by various processes in situ, with the rock at its location. And so it's breaking rocks down through whatever process, and then once the rock is broken down into sediment, then that sediment can be transported by a variety of mechanisms, and those of course are processes of erosion. So weathering is the breakdown of rock, erosion is the transport or the removal or the mechanism that actually moves that sediment into some other location. And there's lots of different weathering processes. We're going to look at a couple of those today. We mainly divide those into two sort of groups, either physical or mechanical weathering processes, and then we have the chemical weathering processes. Erosion, we'll spend more time on each one of these concepts later in the course, but we'll look at how sediment is transported just by gravity when we talk about mass wasting and landslides. We'll look at the role that water plays, both moving water or maybe in an ocean environment. We'll look at wind processes and how the wind can transport and move sediment. And then we'll also spend some time looking at glaciers and the impact that ice can have on transporting sediment. So all of these are different erosional agents, with ice, I suppose, being the most powerful. Gravity is kind of like the common player throughout them, but ice is the most powerful in the sense that it can transport sediment of any size. However, ice is the least common. Water's probably the most common because water's much more ubiquitous on planet Earth. Okay, so let's look at some different physical weathering processes here. How do rocks break down with just basic physical mechanical processes? So the first one we might consider here is what's known as frost wedging. Basically, as we all well know, when water freezes, it actually expands, kind of a weird substance, water. Most things contract in terms of their volume as the temperature drops, and water does the same thing, I think, until you get to like 36, 38 degrees Fahrenheit, a few degrees above 0 Celsius, and then once you get below that temperature, it actually starts expanding, something weird that I totally don't understand, but an interesting phenomenon of water. And that expansion of water as it forms ice actually has sufficient force to actually break rock apart, to infiltrate fractures and cracks and cause those cracks to widen over time through this process called frost wedging. It's really common in mountain environments. So you got a couple pictures here of these rocks actually splitting as the frost wedging takes place. It can actually cause rocks to not only separate over time, but actually topple. And so ultimately the frost wedging taking place with this rock in the top left here might actually cause it to actually fall off this pedestal or this cliff band here and into the abyss below. So let's do a fun little quiz question here right off the bat. So I give you 5 different locations here, and I want you to think about which one of these locations would be best suited to having frost wedging as a significant weathering process. So go ahead and consider those. Maybe pause the video here for a second if you want to give this some time to mull it over, talk to someone in the room next to you, see what they think, and then I'll reveal the answer. So if we look at these options here, I tried to pick places that were, fairly well known. We have Phoenix, Arizona, Miami, Florida, Fairbanks, Alaska, Jackson Hole, Wyoming, and Honolulu, Hawaii. And maybe the 3 that hopefully you took off the list first were Arizona, Florida, and Hawaii. These are very warm climates where Ice rarely, if ever, forms. I don't think, although we could check the climate records, you'd be hard pressed to find a day below freezing in either Miami or Honolulu. Phoenix, Arizona, the town I was born in, they do occasionally get, an odd winter day here or there where there's a skiff of snow and temperatures below zero, but it's pretty scant. There's not a lot of days like that. And so those locations, while they get plenty of water, they don't, well, except Phoenix, I suppose, they don't really have the temperatures below zero enough to cause frost wedging on a significant scale. So then we're left with Fairbanks, Alaska, and Jackson Hole, Wyoming. And Fairbanks, I think if you look at the climate data there, being in the central portion of Alaska, they have large sections of the wintertime where it's just cold. It's below zero for a long time. And for frost wedging to be significant, we would want as many days as possible where we can fluctuate temperatures above and below zero. And so I think, without looking at the hardcore climate data, I think Jackson Hole would be the better choice, because I think you're going to end up with more days in a calendar year where the temperatures are above and then below freezing. As many times as we can go through that frost thaw cycle, that will make it a much more significant process. So I think that's the best answer there. But of course, we can maybe look into the data there and see if I screwed this one up. I don't know. I just threw that one together. Okay, so frost wedging, you again tend to see it in mountainous regions, in the mid latitudes. Of course, at high latitudes it can be all the way down to the coastline, sea level. This might be something you might see. So as the frost wedging is taking place in the rocks up above, that dislodges these rocks. They eventually succumb to gravity, fall down the slope, and this pile of angular loose boulders that you often see on a slope is sometimes called talus. And so frost wedging is a climate dependent process. You need obviously water, but you also need these temperatures dipping below freezing and then rising above freezing as much as possible. Okay, our next physical weathering process goes by a couple different names, but I prefer unloading or pressure release. And the idea here is that we have taken a rock that has formed underground under pressure, brought it to the surface sometime later, and now that rock is in the process of actually expanding outwards because the pressure has been released off of it. I like this diagram right here. So if you imagine this little round mass here is a body of magma, maybe at the time of the dinosaurs, that cools and crystallizes into an intrusive igneous rock, maybe something like granite. And then if we fast forward, maybe in this case millions of years later, the dinosaurs are gone, but people are around. That same mass of rock, which is now exposed at the surface, tends to expand outwards. The pressure's been removed from it. So while it's expanding outwards, it's breaking into these concentric layers or these sort of slabs that sort of break along the surface of the rock. And so here's a picture from City of Rocks right here in southern Idaho that beautifully illustrates this. You can see where the fractures are. The rock is breaking into layers, not because the rock internally has those layers. This is a granitic rock, but because as the pressure is released, it tends to break along these concentric surfaces that are parallel to the overall surface of the rock layer there. And this can create over time these big kind of rounded features we call exfoliation domes. So here's one near Austin, Texas, Enchanted Rock, another rock outcropping made out of granitic or igneous intrusive rock. So you can see these slabs starting to break apart, some thicker pieces over here, but all that weathering again is part of this unloading or this pressure release. Another iconic place where we see this is in Yosemite National Park in California, a place like Half Dome. These granitic rocks here formed miles underground. Now they're at the surface, and so they tend to expand outwards. In this inset photo in the upper right, ignore the people, although they give the photo a sense of scale. This is up the backside of Half Dome, the Cables Trail. But look at the rock here. Look how it's breaking along these thin fractures that are parallel to the surface. It's basically peeling like layers of an onion. It's exfoliating just like your skin. And so you could go up here with, don't do this of course, but if we chipped away and broke away all these slabs, these seemingly loose pieces, and cleaned this off, it would only take some number of years probably for new ones to develop, because this exfoliation or unloading process is an ongoing and dynamic process. We get things like root wedging, so just the growth of organisms in cracks or voids or pore spaces in the rock, as those root systems grow and develop, that can actually split the rock apart. So you would think that, rock versus tree, that the rock would win, but this is actually a case where the organism, the plant in this case, is able to split apart the rock as it grows. It starts as a little seed in a little kind of crevice, and then it gets watered and germinated, and it starts to grow, and over time it can actually split apart the rock. So this is considered a physical weathering process as well, even though it involves a little bit of a chemistry kind of thing. And this is called salt weathering. I think that's probably the best name I know for it. It might go by some other names as well, but it's these holes you tend to get in rocks. A lot of times people think they're gas bubbles, but those would only, of course, form in igneous rocks, and they tend to be a lot larger than that in many instances. But this is when we have either salt or calcite or some soluble mineral that has been transported with water into the pore spaces of the rock. The water evaporates, but as the crystals from that mineral start to grow, it actually breaks apart and splits the rock apart, and it can tend to produce this kind of honeycomb weathering, or it's also called tafoni. It's an Italian word, and this one here I think is from Capitol Reef. A lot of times you see this in coastal locations because you have the salt from the ocean, but even in inland locations you can get this as well. In kind of where I live here in southern Idaho, the Great Salt Lake's not too far away from some areas, and so you can get it transported from the salt flats down in Nevada or in Utah. And even in places like here in Capitol Reef, the rocks themselves might contain some calcite or some salt that can be dissolved and then transported with water later by rivers and streams or just rain, and then reprecipitated. And again, as those crystals form, that breaks the rock up into these very attractive and kind of fun to look at holes in the rock. So salt weathering, another physical weathering process. If we look at our chemical weathering processes, there's a couple here I'd like to highlight. So oxidation is a very common one. Anytime you have iron, any mineral or material that contains iron, it can readily react with oxygen, which is essentially just turning it to rust. This is exactly how something metallic, if you leave it outside or you're in a very wet climate, something might rust very easily. This is just oxidation. This is why we see in places like Arches National Park here in southern Utah these beautiful red rocks, these sandstones that are this reddish or orange hue. And you might ask yourself, well, why is it that color? Because when you look at the sandstone up close, what you find is that the grains of sandstone are mostly made out of quartz, and quartz is mainly a colorless mineral. It's certainly not red typically, and so if you looked at it under a hand lens or a microscope, you'd find these mostly colorless rounded grains of quartz. But what's cementing those quartz grains together is an iron-bearing mineral, hematite. And so this oxidation process can both weather the rocks, but it actually can form cement that holds the rocks together as well. And so it's actually the cement in this case that actually imparts the color we see on some of these beautiful sandstones and red rocks that we see in this sort of landscape here. Another chemical weathering process is dissolution. So remember, one of the minerals we learned was calcite, and calcite, along with a few other minerals, is important because it's soluble. It can be dissolved in water or even in slightly acidic water. So when it rains out of the sky, H2O, that water passing through the atmosphere picks up and some CO2, some carbon dioxide, and it dissolves it in with the water and forms, this is a carbonic acid. It's basically a weak acid. So what falls to the ground after it rains isn't pure water. It's actually a weak acid. And in the presence of these rocks that are soluble, like limestone or marble, and there's some others too, like gypsum, it can actually dissolve the rock over time. So it's chemically weathering the rock over time, and it might make the ground kind of pitted like this. In some environments it forms caves, and that's a topic we'll study later when we look at groundwater. In desert environments it might make the rock kind of pitted but very sharp. When we go rock climbing on this stuff, you definitely know it because the rock can be quite sharp on limestone in these more arid types of climates. So dissolution is another big chemical weathering process. And so all of our weathering processes are going to depend on some other factors that will contribute how quickly they occur or how quickly they progress. And one thing is just how how much of the rock is exposed. And I love this little diagram here. So if you take a cube of rock, you have 6 sides, right? 6 sides to a cube. That means that the weathering processes can only really attack it on those 6 sides. But if you take that same cube and break it up into 8 smaller cubes, well, now each one of these 8 cubes has 6 sides. That's 48 faces of the rock. And so we've got more area of the rock, more opportunities for the weathering to break down the rock. And if you took those cubes and broke those up even more, you'd have even more faces exposed to the weathering processes. So the point is, as rocks break down into smaller and smaller pieces incrementally over time, the weathering rates tend to accelerate to some degree. This is also a fun photo to consider too when we talk about weathering rates. These are 2 tombstones in the same cemetery. I think, if I remember right, this is somewhere in the eastern US, maybe like Kentucky, Tennessee, something like that. So the tombstone on the left, you can read everything, the person's name, date of birth, date of death. And then if you look at the one on the right, it's hard to make out any of the details there, although you might be able to pick out right here the same year of death, 1888. So assuming these 2 tombstones were erected in about the same year, which I believe they were, you can see the degree of weathering and the difference there between the 2 tombstones. The one on the left, of course, is made out of granite or something similar to granite, much more resistant to chemical weathering. The one on the right looks like it's probably made out of marble, and so they've selected, once upon a time, marble as the tombstone rock type, but you can see how the chemical weathering processes have rendered this mostly, it's definitely hard to read, if not impossible to read, just over that 100+ year increment. So the type of rock that we see will greatly impact how quickly weathering takes place. Some rocks are very resistant to weathering, some are much more susceptible to weathering. You might remember Bowen's reaction series. We studied this in looking at igneous rocks and the order in which minerals crystallize from magma, but this fun little graphic here also has some implications to weathering. It turns out that the last minerals to crystallize, as we work our way down Bowen's reaction series, the low temperature minerals, the minerals that are stable at these low temperatures, these tend to be more resistant to weathering. They tend to not weather as quickly as those up here, the high temperature minerals. These tend to break down much more quickly due to various chemical weathering processes. So a fun little example there of how this Bowen's reaction series actually fits in a little bit with chemical weathering from minerals like quartz, which are very abundant, partly because they're hard and they lack cleavage planes and they're common, but also because they're very resistant to weathering. Quartz is a mineral that can get recycled over and over and over from one environment to the next. Other things that affect the weathering rates, the climate is a big factor. Basically, if you have areas with high temperatures and more precipitation, more moisture, they tend to have more enhanced weathering rates. You've got more vegetation. The vegetation in the soils can increase the acidity, and everything just speeds up quite a bit. So the climate is an important factor to consider when looking at weathering rates. And then finally here, to wrap up this episode, some of the most fantastic things people see and often have questions about, and things that I often field as questions from the public, involve rocks that look like this, just these interesting shapes that ultimately a lot of times the answer to their questions is something involving what we call differential weathering. Basically, rock types that are different, and the rate at which they're weathering is quite a bit different. So here's me with some students many years ago down along the Utah-Arizona border, this area called Cliff Dwellers, right near the start of the Grand Canyon and Lee's Ferry. And you can see these big sandstone boulders resting on these very small pedestals of mudstone. And so the fact that these sandstones are much more resistant to weathering, they're actually kind of protecting, it's like a little umbrella protecting these mudstones, which do get weathered by surface runoff, but not as readily by water falling vertically down out of the sky. Same thing here in the upper right photo. This is Goblin Valley. You've just got a little bit more resistant unit on the top there. Probably, again, a sandstone, fine-grained sandstone, probably in this case, and some mudstone here. So you end up with this fun little kind of mushroom capstone looking feature. And a place like Bryce Canyon National Park is another great place to to look at when talking about differential weathering. These hoodoos, these iconic rock formations that make up Bryce Canyon National Park. If you look at these closely, you'll see that there's sets of vertical lines going through a lot of the cliffs here, and there's also sets of horizontal layers as well. And so the weathering of these hoodoos is fundamentally related to the rock type. This is all limestone, kind of a dirty limestone. It has some sediment in it. But then these vertical fractures, or what we call joints, and then the beds, the layering that's inherent to the rock as well. And if you just add in all the freeze-thaw cycles, Bryce Canyon sits at 8,000 feet, plus the heavy monsoon rains that they get. They've just got the perfect combination of factors in terms of inherent rock characteristics and external climate and weathering factors that lead to the formation of these fun little hoodoos. So hopefully that helps a little bit. There's obviously, with a lot of these topics, you can deep dive. This is just Geology 101, so we're just hitting some of the basic processes here. But hopefully you've enjoyed this episode. And in our next episode, we'll tackle the sedimentary rocks and sedimentary processes. Now that we've learned how sediment is created, we want to learn a little bit more about how sediment gets deposited, how it gets laid down and actually turns into rock. So thanks for joining me on this episode. Appreciate your support of the channel. There are ways to donate to this geology education series. There's links underneath the video description. There's also the little thanks button down to the right of the viewer. Please make sure you subscribed and liked and do all those good things, and appreciate your time. Take care.